Hello and welcome to this video on quadratic sequences. In this video we're going to look at some quadratic sequences and we're also going to find the nth term of some quadratic sequences. But before I start talking about a quadratic sequence fully, I just want to cast your mind back to linear sequences. So you will have seen linear sequences. So an example of a linear sequence may be 5, 9, 13 and so on. How do we know that this is linear? Well, if you look at how much each term goes up by, well, that's 4 and that's 4. So then we would find the nth term for this sequence. So we know that it would be 4n, and then we want the 0th term, so we would take 4 away. 5 minus 4 is 1. So therefore we know that our nth term for this sequence would be 4n plus 1. So this is a little bit of a side note, but we know that an nth term of a linear sequence, so algebraically, so where there's no numbers, will generally look like this. So that would be the sort of general way of writing it. We say general because there's a letter, so the coefficient of n here is a letter, so that will take the value of a number. So if we can compare the sequence we've just looked at to this general form, the 4, or b is equal to 4 there, and c would be equal to 1. So as you can see, it's linear because the n here isn't squared or cubed or anything, it is just to the power of 1. So it is linear, a linear term. So let's have a look at an example of a quadratic sequence. One that you may have seen before is this very famous sequence. So 1, 4, 9, 16, 25. So this should look really familiar. And it is of course just the square numbers. So 1 squared is 1, 2 squared is 4, 3 squared is 9. And obviously so on. So what is the difference between a linear and a quadratic sequence? Well, we can see here that the difference between 4 and 1 is obviously 3. The difference between 9 and 4 is 5. The difference between 16 and 9, well, that's 7. The difference between 25 and 16 is 9. So as you can see, we don't have, like our linear sequences, our sequence going up by the same amount every time. We don't have that anymore. They go up by different amounts, so 3, 5, 7 and 9. So that's what the difference is. And we obviously need to be aware of this so we can identify whether our sequences are either quadratic or linear. And then later on in the video, we're going to see how we can calculate what the nth term is. So another example of a quadratic sequence, so 2, 8, 18 and then 32. So again, we look at the differences between successive terms, so successive being the next term. So the difference here between 8 and 2 is 6, then it's 10, and then it's 14. So again, we see that there isn't a constant amount, so that means it can't be a linear sequence, it must be a quadratic sequence. Looked at sequences that are quadratic and increase, but can we have a sequence that decreases that is quadratic? Because we sometimes see that with the nth term for linear sequences, that we can have sequences such as 10, and then the next term is 5, and then 0 and minus 5. And can we have that for quadratic sequences? Well, yeah, of course. Example of that would be 99, and then we go to 94, then 85, and 72, and so on. So the difference between 9 and 94 is obviously minus 5. The difference between 94 and 85, well, that is minus 9. And the difference between 85 and 72, That's minus 13. So that's an example of a sequence that's quadratic that decreases. So in the next part of the video, we're going to look at the nth term for these quadratic sequences. So at the start of the video, I told you that for the nth term, our sequences are of the form Bn plus c. So that's linear. An example of a linear, so the general form, of a linear sequence is Bn plus c. So examples of that are 4n plus 2, could have minus 3n plus 7. So anything that is of the form Bn plus c. So in that case, what does a quadratic sequence look like? Well, obviously it's going to be very similar, but it does have a slight difference. So the difference is that it's an squared, and really we expected to see a squared because we're talking about quadratic. So x squared is a quadratic and y equals x squared is a quadratic graph. So we expected to see something squared. So that isn't something that we should be puzzled about. And then the rest of it is plus Bn plus c. So that is an example of the general form of the nth term for a quadratic sequence. So we could have an example such as 2n squared plus 2n. That would be an example. We could have n squared itself. We could have n squared plus n. Or if we really wanted to, we could have something with all three parts of this. So we could have a question that was, I don't know, 4n squared plus 2n plus 1. So that would be an example. So for each of these examples that I've just written out across here, I'm going to work out the first few terms just to show you how we do that. So I'm going to set up a little table. So 2n squared plus 2n. We've got n squared. Then we've got n squared plus n. And then our last one was 4n squared plus 2n plus 1. So I'm just going to work out the first three terms just to show you how we do this. Just draw out a little table. Okay, so all we do is if we want the first, second, third, obviously these sequences just keep going, so they would have more terms. But if we just want the first, second and third terms, we just substitute 1 into there. So every time we see n, we just substitute 1 in to find the first. So it would be 1 squared times 2 plus 2 times 1. So that would be 4. Then again, if we want the second term, we just substitute 2 in where we see n. So in that case, we'll have 2 times 2 squared plus 2 times 2. That's 12. And then if we want the third term, again, every time we see the n, we just substitute 3 in. So we'll have 2 times 3 squared plus 2 times 3. And that is 24. So for n squared, if we want the first three terms, well, we'd have 1 squared, which is 1. We'd have 2 squared, which is 4. And we'd have 3 squared, which is 9. We obviously already saw that in the previous part of the video. Moving on to this quadratic sequence, n squared plus n. If we substitute 1 in, we'll get 1 squared plus 1, so that's 2. If we substitute 2 in, we'll get 2 squared plus 2. Well, 2 squared is 4 plus 2, that's 6. And then for the third term, we'll get 9 plus 3, and that is, of course, 12. And then for this monster at the end, 4n squared plus 2n minus 1. So we get substituting 1 in, we get 4 times 1 squared plus 2 times 1 plus 1, and that is 7. If we want the second term, we do the same thing, we just put 2 in. So for that, 21. And then if we want the third term, again, we just put 3 in place of n. So substitution, I got 43 for that. So that's an example of finding terms in quadratic sequences. So now we're going to have a look at finding the nth term of quadratic sequences. So just very quickly, because we're going to need this, we know that the nth term of a quadratic sequence should be of the form an squared plus bn plus c. So we're looking for something that looks like that. Okay, so if we had the sequence 1, 4, 9, 16, this is obviously a sequence we've already seen. So what we do is we find the first difference, so the difference between successive terms. So the difference between 1 and 4, well that's 3. The difference between 4 and 9, well that's 5. And the difference between 9 and 16 is 7. So that's our first difference. Then, after that, we need to find our second difference. Our second difference here, well, the difference between 5 and 3 is 2, and the difference between 5 and 7 is 2. So that's our second difference. And what is the point of doing that? Well, the amount that our second difference goes up by for a quadratic sequence will always be the same amount. So in this case it goes up by 2, but it will always go up by the same amount. So it could be 3, it could be 5, it could be minus 7. It will always be the same amount. And then that will give us what A is. So A is equal to the second difference. I'm just going to put diff for difference. So the second difference divided by 2. So it's half of that number that is the second difference. So in our case, it's going to be 2 divided by 2, and we know that that is 1. Therefore, A is equal to 1. So that means for our sequence now, we've worked out what A is, so that's fine. But we need to work out what the values of B and C are. So that's what we need to do now. Okay, so what we will do here is we'll set up a little table. So we'll have first term, then we'll have our second term. We'll just do the first 3 terms again, just like the table we did earlier. And then we'll have our third term. So we're drawing a little table. Okay, so this was our original sequence, 1, 4, 9, 16, so we'll put original. Well, the first term was 1. The second term was 4. And the third term was 9. The fourth term is 16, but we're not going to worry about that for the time being. And then what we write underneath that is this part. So the first part of what we've just worked out. So we've got to use what we've just worked out to help us now. So that's why we need that to be right. So we said that A was equal to 1. So the first part here is going to be n squared. Because A was 1, we don't really write the 1 in maths before. So the first part. So then we write n squared here. Then what we have to do here in our table is put 1 into this, 2 into this, and 3 into this, just like we'd done in the examples before. So 1 squared, well, that's 1. 2 squared, well, that's 4. 3 squared is 9. So as you can see, we've got the same values. So then what we have to do is we have to do our original sequence minus the n squared sequence. So we're minusing this line minus this line. So this line minus the n squared line. So 1 minus 1, well, that's 0. 4 minus 4, that's 0. 9 minus 9, that's 0. So that then means if we have zeros here, that there is no b and c part, there are no numbers, so b and c are both equal to 0. So the nth term of the sequence, so nth term of the sequence is just n squared. So we worked out the values of a, and then b and c from this little table are both 0. So the nth term is just n squared. And we're going to look at some more examples so that we can really solidify this method, and then we know how to work out the nth term for several sequences. So now we're going to look at a slightly different example, and that will be the example where we have a sequence that is 2, 6, 12 and 20. Okay, so like before, we jump straight in. We need the difference between the first difference between the terms. So the difference between 6 and 2 is 4. The difference between 12 and 6, well, that's of course 6. And the difference between 20 and 12, well, that's 8. So then we say, what's our second difference? Well, the difference between 6 and 4 is 2, and the difference between 8 and 6, well, that's 2. So what did we say? Well, we said that a was the second difference. So the second difference divided by 2. Well, the value of the second difference here is 2. So it would be 2 divided by 2, which is equal to 1. Therefore, a is equal to 1. Okay, so then we set up our little table. So we have the original sequence on top. So that would be 2, 6, 12 and 20. So that's our original sequence. And then, so let's put original. And then because a was 1, and we're using an squared plus bn plus c as our general form of this nth term for the quadratic sequence, we substitute what we know in. Well, we know that a was 1. We've got n squared so far. And then we ignore the rest of it because that's what we're trying to work out. So then we find the values of n squared. Well, that was our first term. So this is our first. This is our second. And then third. And fourth and so on. So if we want the first term of n squared, well, that's 1. If we want the second term of n squared, that's 4. If we want the third term of n squared, well, that is 9. And then the fourth term of n squared, well, that is 16. Then what we did was we did our original minus n squared. So 2 minus 1, well, that's 1. 6 minus 4, well, that's 2. 12 minus 9, that's 3. And then 20 minus 16 is 4. So now we've developed a new sequence. And this is a slightly different example to the one that we've done before, because before we just got zeros for this subtraction that we've done, but now we've got another sequence. So then what we have to do is just find the nth term of this sequence, and that will give us what bn plus c is. So the nth term of this sequence that we've just developed, well, that goes up by 1, that goes up by 1, that goes up by 1. So far we've just got n. Then the 0th term, well, 1 minus 1, so minus 1, well, that'd be 0. We've got n plus 0. So that, what we've just worked out, is the bn plus c part. B, of course, is 1, because there's nothing in for the c part, it's just 0. So therefore, our nth term for this sequence is n squared, which is what we worked out earlier, plus bn. Just like that. And again, we're going to look at another example so we can really solidify our knowledge here. Have another example. So 4, 12, 24, 40, and so on. Okay, so we're going to find the nth term of this sequence. So you probably get the drill by now. First thing we need to do is work out our first differences. So the difference between 12 and 4, well, that's 8. The difference between 24 and 12, well, is 12. And then the difference between 40 and 24 is 16. So that's our first difference. Then again, we find our second difference. So the difference between 12 and 8 is 4. The difference between 16 and 12 is 4. So for our general nth term, which is an squared plus bn plus c, from what we talked about earlier, we know that a is half of that second difference. So that will be 4 over 2, which of course is just 2. So we know what a is. So therefore, so far, we have 2n squared plus bn plus c, like that. So we haven't worked out what bn plus c is. So we haven't worked out the values of b or c. We know what a is, of course. That's why we use our table. So we jump straight into our table. So we take our original sequence. So that was 4, then it was 12, 24, and 40. Now, in the other examples, a was equal to 1, so we had n squared as our row here. But now we've got 2n squared. So we're not going to be using n squared anymore. We're going to be using 2n squared. And again, this first column is our first term, that's our second term, that's our third term, that's our fourth term. So the first term, so we just substitute 1 in, so that'll be 2 times 1 squared, well that's just 2. Then our second term, well that will be 2 times 2 squared, so that's 2 times 4, which is 8. And then we'll have the third term, so that'll be 2 times 3 squared, which is 18. And then we'll have, for the fourth term, we'll have 2 times 4 squared, so that will be 16 times 2, which is 32. Then, like before, we just do our original sequence minus the 2n squared part. So 4 minus 2, well, that's 2. 12 minus 8 is 4. 24 minus 18, that's 6. And then 40 minus 32 is 8. So we've developed a new sequence there. What did we have to do? We had to find the nth term of that sequence. So that goes up by 2, that goes up by 2, that goes up by 2. So the nth term so far will be 2n. Then we find our 0th term by subtracting. Well, 2 minus 2 is 0, so we're left with 0 again. So then we have our answer. we know from the work we've done to find the b and the c part that our answer is 2n squared plus 2n plus 0. So that is of the form an squared plus bn plus c. We don't write the 0 in maths, so we just leave it as 2n squared plus 2n. Now, something that I haven't said yet that is worth noting, and something I would encourage you to do after you work out these sequences and the nth term for these sequences, is just check that if you put numbers into this sequence that you get the right answer out. So if we wanted to find the third term, we would substitute 3 in, like we'd done previously. So that would be 2 times 3 squared plus 2 times 3. Well, 2 times 3 squared is 18. And then plus 2 times 3, so plus 6. Well, that is 24. So we know that we must have done it right because our answer is giving us values from the original sequence. Okay, so we're just going to look at one more example now. So this example is 4, 15, 32, 55, and 84. Okay, so again, like we've been doing all along, we find our first difference. So that would be 15 minus 4, so that's 11. Then 32 minus 15, so the difference between those is 17. And the difference between 55 and 32, that's 23. And then the difference between 84 and 55, that is 29. So that's our first difference. Then we find our second difference. The difference between these numbers is 6. The difference between 23 and 17, well, that's 6. And the difference between 29 and 23 is 6. Again, like I said before, we should be getting the same number out for the second difference. It should be going up by a constant amount for our second difference. So we want something that is of the form an squared plus bn plus c. How did we find a? Well, it was half of the second difference. So the second difference was 2. So the second difference was 6. So we half that, and we're left with 3. So a is equal to 3. So what we know so far is that we've got 3n squared plus bn plus c, like that. So then we set up our little table. So the original sequence was 4, 15, 32, 55, and 84. Then we take this 3n squared part, and we have to find out the first, second, third, fourth, and so on terms. And again, why are we doing that? Because it will give us the bn plus c part. So if we take the 3n squared part away from the original sequence, it will give us what's left, which is the bn plus c part. So the first term of 3n squared, well, that is 3. The second term is 12. The third term is 27. The fourth term is 48. And then the fifth term, that's 75. What did we do then? Well, we subtracted. So the original minus 3n squared. So 4 minus 3, well, that's just 1. 15 minus 12, that's 3. 32 minus 27 is 5. That's a really dodgy 5. 55 minus 48 is 7. And then 84 minus 75 is 9. So we've developed a new sequence. We then find the nth term of that sequence. The difference between these numbers is 2. 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 So far we know that we've got 2n. And then we find the 0th term. So we take away 2. 1 minus 2. That's just minus 1. So we've got minus 1. And then that is our Bn plus C part. So that was what we didn't know from up here. So we didn't know that. So then we use this table to work that out using the procedure of taking our 3n squared, then minusing, and then finding the nth term of that new sequence. So that gives us the Bn plus C part. So then our nth term, so our final answer is 3n squared plus 2n minus 1. Again, I am a big fan of checking the answer just to see whether it's right. So if we wanted the 4th term, we'd just substitute 4 in, so the 4th term. So we substitute 4 in, so we get 3 times 4 squared. Well, that's 3 times 16. And then we get that, and we'd add 2 times 4. Then we're taking away 1 at the end. That, when we work that out, gives us 55. So we know that we must have done it right because we've substituted to check that our answer is correct.